In previous video, we discussed about the PLL and general applications of PLL. We have seen the block diagram of PLL and the functionality of each block, and also we have seen the transfer characteristics of PLL. So through transfer characteristics and some real life examples, we try to understand how the PLL works. So just to remind or recall the concepts, we have seen that PLL always enters into free running mode first, then enters into capture mode, and once it acquires the lock in the capture mode, it will not leave the lock at the end of the capture range, but it waits till the end of the lock range. So it maintains the lock throughout the lock range and leaves the lock at the end of the lock range. So this is always the functions of the PLL. It always enters into free running, then establishes the lock at capture range, maintains the lock throughout in the lock range. So if you remember the definitions, we have defined the capture range as the range of frequencies over which initially unlocked PLL acquires the lock. And while defining the lock range, we have defined as the range of frequencies over which the PLL maintains the lock, because lock is already established. Now it has to maintain, so maintains the lock. So we have seen the characteristics and we have defined these three parameters: free running frequency, capture range 2 times delta FC, and lock range, that is 2 times delta F. So last time I was trying to show the simulation, but because of lack of time, I could not show it. So first, we'll see the simulation through which we'll try to understand the concept of the PLL. So here is the simulation. So as I was talking, there is a virtual PLL which is available in the mixed virtual. You can search in the component, go to the mixed, and then there you can find out the virtual PLL. So here I have set the parameters as VCO free running frequency, which is very important parameter, that I have set it to 1 kilohertz. So that is F0. Low pass filter cutoff frequency I have set it to 0.1 kilohertz. So all these parameters you need to just set. VCO output amplitude I have set it to 5 volts, and phase detector gain, which is volts per radian, this is set to 0.25. So out of this, very important parameter is this 1 kilohertz, and the cutoff frequency I have set it to say 100 hertz. So depending upon cutoff frequency, the band is going to change. So once you set these parameters, here you can see the connections. There is VCO output which we are going to observe. So blue. So I have connected here oscilloscope. Now from this I am giving PLL input. Okay. So this is function generator. Now right now I have set the function generator frequency as 1 kilohertz. This is a sinusoidal PLL. So I am giving a sine wave here. Output will be also sine wave. And don't forget that there should be a feedback. So there is a phase detector input and phase detector output. Output of the phase detector, we have to give it back into the phase detector input for comparison. So this is how you can give the feedback. We are not interested in low pass filter output. So let us simulate. So right now I am giving 1 kilohertz frequency. So if I start the simulation, you can see that VCO frequency, which is blue, okay, is almost matching with the input frequency because this is 1 kilohertz, and that's why you can see that there is a perfect locking condition. Now let me change this frequency, and I will change it to say 900 something, 900 hertz, and let us simulate again. So now you can see two different signals. So one is input that I have given, and blue is VCO output. Now here you can see that still this frequency is very close to the free running frequency. So now I will go on increasing this so that you can see the tracking. So let me increase this frequency in steps. So PLL action is initiated. So you can see that PLL started its changing its output. Now it is hardly, rather it is difficult to notice the change, but later on you will definitely see because I am gradually changing this frequency and slowly approaching to the 1 kilohertz. Let me apply 990 hertz and again simulate this. So it's very close now. So there is very small phase difference you can see, and it is tracking. So it is continuously monitoring the phase. As soon as I make this 1 kilohertz, so let me make this 1 kilohertz, which is exactly equal to pre-running frequency. You can see that both the frequencies are perfectly overlapping, and that's why you cannot differentiate between input and output. So this is perfect locking condition. Now here, after, if I go on increasing the frequencies further, say what 1.2 kilohertz, and let me simulate again, you can see that still it is tracking. So still it is matching this, trying to match the frequencies. So if you stop and see, then both the frequencies are almost same, although there is a phase difference. But now let me increase this frequency to say 2 kilohertz, so which is definitely greater than this, and simulate again. Okay, so now you can see that input frequency is almost 2 kilohertz, but output frequency is now equal to free running frequency. Can you observe this blue? So it is free running frequency. So PLL are already entered into free running again. So hereafter, if I change the frequency, say 3 hertz, 3 kilohertz, or 4 kilohertz, you can notice the input frequency is varying, but output is not responding. So PLL is not responding, PLL is not taking any action, and it is oscillating with its own frequency, that is blue, which is equal to 1 kilohertz. So this is what we have seen in the characteristics of PLL, transfer characteristics of PLL. So I repeat, now it is in free running mode. We have seen that a perfect locking mode when 1 kilohertz input frequency was matched with the uh, frequency of VCO, free running frequency of VCO. And in between, when input frequency was very close to F0, that is within the capture range and lock range, that time also you must have noticed that output was tracking. So somewhere again, if I have to show, let me give as 1.1 kilohertz. So you can notice now that PLL output is almost same as PLL input. So although there is a phase difference, both the frequencies are matching. So this is what the tracking of the PLL. This is how the PLL works. So I repeat, this is a virtual PLL. This is not actual IC, just like IC 565 that we are going to see. So hope you have understood this demonstration, and through this demonstration or simulation, hope the concept of PLL is very clear. So let us go back to the PPTs and continue the discussion. So let us see the IC565, which is a popular VCO, popular PLL that you come across in the literature. There are other VCO, other PLL ICs also. But this is quite popular PLL IC and very simple to understand also. So this is a layout. This is pin diagram of IC565. So if you see the literature of our data sheet of IC565, you will find the preamble for this. So LM565 and LM565C, C stands for commercial, are general purpose phase lock loops. So they are general purpose phase lock loops containing a stable, highly linear voltage control oscillator. So linearity of VCO is very important. And for low distortion FM demodulation, this is basically aimed for. So this is one of the application of IC565. Of course, IC565 can be used for other applications, AM detection, FSK demodulation, as well as frequency multiplier. But mainly for low distortion FM, this was the main target that you can find in the literature. Now power supply ranges from plus minus 5 to plus minus 12. So this is a dual supply operation, as you see here. Pin number 10 is plus VCC, pin number 1 is minus VCC. So here we give minus VCC voltage, and here we give the plus VCC voltage. These are the VCO components, resistance R1 and C1. These are the timing components, timing capacitor and timing resistor. So through this R1, C1, we can set the frequency of VCO. So if you look at the pin diagram, here and here, the same pins you can find here. So this is a functional block diagram, you can see. So as you see in the PLL block diagram, you have phase detector. Okay. So there are two inputs for phase detector, and there is a special third input for phase comparator, which is specifically devoted for VCO. That means if we have to give the VCO output, so the output which is coming out of VCO, it is available at pin number 4 externally. This we can give as a feedback to pin number 5 by external connection. So explicit connection we have to do it here. So that closes the feedback. Right now it is in open loop. Okay, fine. Then the second block, actually it is filter, but here you can see the error amplifier first. Doesn't matter because they are in series. So first amplifier comes, and then we have filter. Now here we have here in IC565 they have used a passive filter. So this is R2 3.6 kilo ohm, which is internal resistance which we cannot change. So R2 is going to be fixed, and this is C2, which is called as demodulating capacitor, that is always connected between pin number 10 and 7. So combination of R2 C2, resistance in series, capacitor in parallel, that forms the low pass filter, and that is passive low pass filter. The output of the error amplifier and this or the control voltage, which is available as demodulated output at pin number 7. Now this you need not explicitly give to VCO because there is an internal connection, and the output of this error amplifier, it automatically goes to VCO internally, and then VCO output is available here. So this is about the functional block diagram of IC565.